Welcome to our channel, where we explore the wonders of the universe and beyond. Today, we dive into one of the most fascinating and mysterious objects in the cosmos: neutron stars. These stellar remnants are some of the densest objects known, and recent discoveries have challenged everything we thought we knew about them. Get ready for an incredible journey into the heart of these cosmic giants. Imagine a star so massive that when it dies, it doesn't simply vanish. It transforms into something extraordinary. Neutron stars are born in the fiery crucible of a supernova, the explosive death of a massive star. These remnants are incredibly dense. Just a teaspoon of neutron star material would weigh billions of tons on Earth. But what lies within these cosmic giants? That's a question scientists are still striving to answer. To truly grasp the enormity of neutron stars, let's start at the beginning with the life and death of stars. Stars like our Sun shine by burning nuclear fuel in their cores, fusing hydrogen into helium through nuclear reactions. This process releases immense amounts of energy, which counteracts the force of gravity trying to collapse the star. However, this delicate balance can't last forever. When a star exhausts its nuclear fuel, gravity takes over. For stars significantly larger than our Sun, this end-of-life phase is particularly dramatic. These massive stars, with at least 8 times the mass of the Sun, undergo a catastrophic collapse when their fuel runs out. The core of the star, now devoid of the energy to support itself, implodes under gravity's relentless pull. The outer layers are blasted away in a supernova explosion, one of the most powerful events in the universe. This explosion leaves behind spectacular clouds of interstellar material, rich in dust and heavy metals, the building blocks for future stars and planets. But at the center of this nebula, something incredible happens. The core contracts further, and if the remaining mass is between about 1.4 to 3 solar masses, it forms a neutron star. If the core's mass is greater, it may become a black hole instead. Now, let's focus on neutron stars. These remnants are incredibly dense and compact. Imagine compressing the mass of the Sun into a sphere only about 20 kilometers in diameter. That's roughly the size of a city. The density of a neutron star is so extreme that just a sugar cube-sized amount of its material would weigh about 1 billion tons on Earth. This incredible density raises many questions about the state of matter inside neutron stars. Matter inside a neutron star is squeezed so hard that it exists in forms we can only theorize about. Under this immense pressure, even atoms collapse. Electrons merge with protons to form neutrons. But it might get even stranger. Some theories suggest that the extreme conditions could stabilize more exotic particles that don't survive anywhere else in the universe. Others propose that the intense pressure and heat might melt particles together into a swirling soup of quarks, the fundamental building blocks of matter. To understand what's happening inside neutron stars, scientists use something called the equation of state. This theoretical model describes the physical processes and properties of matter under extreme conditions. The challenge is that we don't yet know which of the many proposed equations of state is correct. Each model predicts different behaviors for neutron stars based on their mass, temperature, and rotation speed. Recently, observations by the European Space Agency's XMM-Newton and NASA's Chandra X-ray observatories have added a new twist to our understanding of neutron stars. These powerful space telescopes detected 3 young neutron stars that are unusual. So, what does this mean for the field of astrophysics? First, let's talk about the implications. These observations suggest that many proposed models of neutron stars might be incorrect. Out of hundreds of theoretical models, only a few may be viable. This discovery could be the key to unlocking the true equation of state for neutron stars, a theoretical framework that describes the physical properties inside these dense objects. Uncovering the correct equation of state is crucial because it helps us understand what happens at the core of neutron stars, where matter is squeezed to extreme densities. Under such immense pressure, the familiar building blocks of matter, like protons and neutrons, could behave in ways we have never observed. This could involve exotic phases of matter or interactions governed by the fundamental forces of nature. To dive deeper into this discovery, let's explore the process behind the observations and analyses. The three unusually cold neutron stars were so dim that only the exceptional sensitivity of XMM-Newton and Chandra could detect them. The research team, led by astrophysicist Nanda Ria at the Institute of Space Sciences, analyzed the X-ray data to determine the temperatures and other properties of these neutron stars. Step 1 involved measuring the physical properties of the neutron stars. By studying the X-rays emitted from their surfaces, scientists could infer their temperatures. The sizes and speeds of the surrounding supernova remnants helped estimate their ages. This step was crucial because understanding the cooling rates required accurate age determinations. Next, the team computed cooling curves for different neutron star models. These curves predict how a neutron star's temperature changes over time, depending on various factors like mass and magnetic field strength. Each model incorporates different cooling mechanisms, such as neutrino emission or superfluidity within the star's core. Finally, using machine learning, the team compared the observed cooling rates with the predictions from different models. They found that most proposed equations of state could not account for the rapid cooling observed. This means only models with a fast cooling mechanism could explain these findings. This statistical analysis was essential in narrowing down the viable models and excluding those that didn't fit the data. This research is a significant leap forward in our understanding of neutron stars and the fundamental laws of the universe. It showcases the power of teamwork and the integration of different scientific disciplines, from particle physics to astrophysics and beyond. The findings not only challenge our existing models, but also open new avenues for exploring the nature of matter under extreme conditions. One of the most exciting aspects of this discovery is its potential to bridge the gap between two fundamental theories in physics: general relativity and quantum mechanics. General relativity describes the behavior of gravity on large scales, such as the motion of planets and the structure of galaxies. Quantum mechanics, on the other hand, explains the behavior of particles on the smallest scales, like electrons and quarks. Neutron stars exist at the intersection of these two realms. Their immense gravity, combined with the extreme densities within their cores, creates conditions where both general relativity and quantum mechanics must be considered. By studying neutron stars, scientists hope to find clues that will help unify these two theories into a single, coherent framework. This quest for a unified theory has been one of the most significant challenges in modern physics. The behavior of matter inside neutron stars could provide the missing pieces needed to complete this puzzle. The rapid cooling of these newly discovered neutron stars offers a unique opportunity to test different theoretical models and refine our understanding of the fundamental forces that govern the universe. But the story doesn't end here. We want to hear from you. What do you think about these findings? How do you believe this discovery will impact our understanding of the universe? Drop your thoughts and questions in the comments below. Your curiosity and engagement drive the exploration of these cosmic mysteries. Here are some questions to spark your curiosity and discussion. What do you find most fascinating about neutron stars and their extreme conditions? How do you think the discovery of unusually cold neutron stars will change our understanding of stellar evolution? What are your thoughts on the potential for neutron stars to help unify general relativity and quantum mechanics? What other mysteries of the universe do you hope to see solved in the future? If you enjoyed this video, don't forget to like, share, and subscribe for more exciting journeys into the cosmos. Hit the notification bell so you never miss an update. Together, let's continue to explore the universe, one discovery at a time.